In this video, we're going to do optimization on the volume of a trough whose cross-section is a trapezoid. And what's happening is we're starting off with a sheet of metal that's 4 by 24, and the two edges are going to get folded up to make the trough. So there's a bend here, and there's going to be a bend over on this side as well. Those sides get folded up to make the trough. Those bends are going to be 2 feet apart, which makes this piece 1 foot and this piece 1 foot. What we want to do is find the theta that will maximize the volume. Right away, that tells us we want to get volume as a function of theta. Well, let's start off with just getting a formula for volume for this thing. It's going to be the area of the base times, we'll call it the depth or the length. Now, the area of the base is a trapezoid. Area of a trapezoid is the height of the trapezoid over 2 times base 1 plus base 2. Okay, we're going to need to label all this stuff, and we'll do that here. Let's do that now. So here's our trapezoid, and we'll just look at the cross section. Remember, we know this is 2 feet, and this side here we don't know. So we might want to give this a name. For instance, we might call it X, because that's going to vary. And this again is 1 foot, and this side here is 1 foot. So, oh, and we need a height of our trapezoid, which if we want, we can keep as H for right now. So we have H, oh, we haven't finished off our volume, excuse me. Area of the trapezoid times the depth, which is constant, which is always going to be 24. Now, let's try this again. This is going to be, in terms of our labeling, H over 2. Maybe we make this side B1, the bottom base, so it's a constant. It's always going to be 2, so it is just 2. It doesn't need a variable. Plus our other base, which right now we're calling X, times 24. We can simplify the 24 and the 2, and let's write this for right now as 12H times 2 plus X. Now remember what we were saying. We want to maximize the volume with respect to theta, right? That theta is the angle right here. So let's see if we can get our X and H in terms of theta. So what I'm going to do is make a little bit bigger. And there's our angle. This part here we're calling H. This part here we haven't given a name yet. I'm just going to call it A. We could call it whatever we want. But now we can get theta in terms of H and A. And we'll see the value of that really quick. H, obviously, it's in our volume. A isn't, but we'll see how we can make it work. So first off, H is the opposite side, so sine of theta equals H over 1. So sine of theta equals H over 1, or just H. That works out very nice. And cosine of theta, very similarly, equals A over 1, or just A. Now again, we know how H fits into our function. Let's talk about how A does. Well, notice what A is. A is that piece right here. It's underneath the fold. So this is A, and this is A. So notice that X is the 2 feet plus an A on this side and an A on this side. So X equals 2 plus 2A, or 2 plus 2 cosine of theta, because A is equal to cosine of theta. Now we can get our volume in terms of theta. So first off, here's my first substitution. So I have 12 sine of theta. And now my other one, I'm putting this in for X, so times 2 plus 2 cosine of theta equals 12 sine theta. Oh, and I'm missing a 2. 2 plus 4 plus 2 cosine of theta. I forgot this 2 here, and then we're putting in 2 plus 2 cosine theta for x. Equals, I'm going to distribute this guy, and I've got 48 sine theta plus 24 sine theta cosine theta. Alright, and there is our volume as a function of theta. This is what we want to maximize. Let's take the derivative. Now think about what theta needs to be. Clearly, theta has to be larger than 0. Also, if theta gets up to 90 degrees, we just have a rectangular box. We don't have that trapezoidal shape. So theta needs to be between 0 and pi over 2. We'll do this problem in radians. So we've now got constrained optimization on a closed bounded interval. We're guaranteed to have a maximum and a minimum. So V prime is 48 cosine of theta plus, I'm going to leave the 24 out and do a product rule on sine theta cosine theta. So the derivative, let's do the derivative of sine theta, which is cosine theta. Leave cosine theta alone. Plus the derivative now of cosine theta is negative sine theta, leaving sine theta alone. So putting this mess together, we got 48 cosine theta plus 24 cosine squared theta minus sine squared theta. As is, this is not going to be an easy equation to solve when we set it equal to 0. But we have a double angle identity right here, the cosine squared minus sine squared. And the one I'm going to choose to use in particular, and the reason I'm going to decide it, is I see that I have cosine theta already in here. I'd like to get this in terms of just cosine theta. Well, I'm going to use the identity 2 cosine squared theta minus 1. All right. There's a couple other double angle identities for cosine of 2 theta. This is the one that I think will work best for us, because now we just have a quadratic. So I've got 48 cosine of theta plus 48 cosine squared theta minus 24. And what I'm going to do is I'm going to factor out the 24 and write it in our quadratic form. 2 cosine squared theta plus 2 cosine of theta minus 1. Alright, now this may look a little bit messy, but what we're going to do is we're going to treat this, if I let u equal cosine theta, then what I have is the quadratic 24 times 2u squared plus 2u minus 1. This can be solved with the quadratic formula. So u equals negative 2 plus or minus the square root of 2 squared, so 4 minus 4 times a, which is 2, times 1, which is c, which is negative 1, all over 2a. Now this will simplify down to negative 2 plus or minus the square root of 12 over 4, which can actually be simplified a little bit further down to negative 1 plus or minus the square root of 3 over 2. Alright? One of these is positive and one of these is negative. Well, we know we want to be in the first quadrant, and we're dealing with, this is a value for cosine, because this is u, which is equal to cosine of theta. So we're only going to need to solve cosine of theta equal to the positive value, which is with the plus. So cosine of theta equals negative 1 plus square root of 3 over 2. Alright. Using an inverse trig function, solving this for theta, we get theta is approximately 1.196 radians, or we'll put this in parentheses, or 68.53 degrees. So we're in between that 0 and 90, like we needed. And so now we look at the absolute max and the absolute min. We're going to evaluate our volume at theta equals 0, theta equals pi over 2, and theta is approximately 1.196 radians. Well, if theta is 0, there is no box at all, so the volume is 0. If theta is pi over 2, it's just a rectangular box because these sides will be straight up, and it turns out that the volume would be 48 cubic feet. Finally, if it's about 1.196, that's where we're going to actually have our maximum volume, because it turns out the volume comes out to be 52.844 cubic feet. So, some interesting things going on in this problem. Hopefully this was helpful.